Hi everyone. Today we're going to cover a number of things in regards to how MSC Nastran handles constraints during the optimization process. And more importantly, we're going to discuss this message you might find in the F06 file on occasion. It goes, run terminated due to hard convergence to a best compromising feasible design. I'll discuss what this means in this video. I'll give you a visual representation of what this looks like for a very simple optimization example. Then I'll give you some terminology that is essential for resolving this issue. Normalized constraints, constraint screening, maximum constraint, and so on and so on. I'll be covering that in this video. And again, my name is Christian. I provide a wealth of training material for MSC Nastran optimization. Please reach out to me at this email address and I'd be more than glad to share this training material. So now let's go ahead and get started. Here on the right is the F06 file for an optimization I performed a while ago. Unfortunately, I have this message at the bottom saying we reached a best compromising feasible design. So let me give you a very simple example of what this exactly means. So here, let me go ahead and scroll down to my example of best compromise in feasible design. So here, let's go over the problem statement for this example first. This surface that you see here is my function f, defined here x1 squared plus x2 squared. My objective is to find the minimum of the surface. And if you quickly glance at this graph, you know that the minimum is at 0. But we have two constraints. We have a constraint function g1 and a constraint function g2. We are saying that x1 and x2 can only be values that satisfy this first constraint. So if you plug in x1 and x2 into g1, you should get less than 1. And the same for g2. g2 should be less than 1. Now, we have a little challenge here. So let me look at the top view of these two graphs. This green ellipsoid represents g1 equal to 1. This red ellipsoid is g2 equal to 1. Every point, every x1, x2 within this first ellipsoid satisfies this first constraint. Every x1, x2 that is within this second ellipsoid satisfies the second constraint. So now the question is, does an x1 and x2 satisfy both constraints? The answer is no. There is no overlap between the constraints, so of course there is no x1 or x2 in existence. In this case, you reach an infeasible design where not all the constraints are satisfied, that is. What MSC Nastran does in this case, it begins at the initial point, as I'm highlighting here, and then begins to move down the surface, and its goal is obviously to reach a minimum. But then once it starts realizing that a solution does not exist, it will actually try and land and end in the midpoint between the constraints or the violated constraints. Here, if I rotate this a little, you can see that the final point is almost in between the two constraints. Now, for this example, how did we resolve it? Let me scroll down a little bit more. It's the same optimization problem statement, but in this case, what I've done is I've increased the constraint for G2. Before it was just 1, but now it's 3. Let's go ahead and look at the two ellipsoids now. The ellipsoid in red is now larger. It's so large that it's actually overlapping with constraint 1. And this is perfect because in this region here are x1s and x2s that satisfy both constraints. And in this case, it does find a minimum. And here, let's go ahead and rotate this a little. You can see as soon as the optimization path bumps into one of the constraints, it rides along that constraint, eventually hitting a minimum for this example. So now, Now that you have an idea of what this visually looks like for a very simple example, let's go ahead and look at the problem that I'm facing right now. And here, let me actually show this in dual views. So here on the left is my F06 file. I should actually detail what my optimization problem statement is first. So let me move the PowerPoint to the right. Then let me show Patron on the left. So this is the cantilever you may have seen before. It's fixed on one end and a point load applied at the other end. There are 4 regions to this plate. So there's a thickness 1 region, a thickness 2, a thickness 3, and a thickness 4. My problem statement is as follows. I want to minimize the weight of this plate as much as possible, but I want to make sure that the tip deflection is between -3 and +3 in the Z direction. And I want to make sure that the von Mises stress on the top fiber of the plate is between -36,000 psi and +36,000 psi. And my design variables are the thicknesses of the plate, so T1, T2, T3, and T4. Now, let's go ahead and ask ourselves, how many constraints have we defined? If you look at the previous slide, it looks like we computed 1 and 2 constraints. But in reality, we actually have created hundreds of constraints. So let me go into more details. For the displacement constraint, we applied the constraint at one of the nodes at the tip. But since we have a lower and upper bound, we've actually applied 2 normalized constraints. In the next slide, I'll define what normalized constraint is. So now for the von Mises stress constraint, how many constraints have we created for that? This plate has over 168 shell elements. And since we applied a lower and upper bound, we double it. So we have actually defined 336 normalized constraints. Now, the question in the air might be, how does MSC Nastran handle so many constraints during an optimization design cycle? Let me go ahead and move this to the right. And here on the left, I'm going to refer to the MSC Nastran optimization user's guide. Specifically, I'll be going to page 4 of the 2016 version. So let's go ahead and navigate to page 40. There's this concept of normalized constraint. What it essentially does, it reduces each constraint to a 1, or rather, it normalizes each constraint. And here, let's go ahead and look at what the constraint or normalization equation looks like. So suppose we were dealing with the upper bound constraint. It would take the current value of, say, von Mises stress and subtract the upper bound of the von Mises stress constraint. And then it would divide it by G norm. Often G norm is the absolute value of either the upper bound or the lower bound. Since we're doing this for the upper bound, it would be the absolute value of the upper bound is G norm. Keep in mind, the rest of the definition gets a little bit more technical. I'll let you read that later on. Now, let's go ahead and apply this equation to an actual value from our optimization. We'll go to the same F06 file, and we'll go ahead and scroll to the very top where we performed our initial analysis. And right now, I'll take a few moments to summarize what MSC Nastran does during the optimization process, just in case you're new to this. So at the very beginning, MSC Nastran enters the first design cycle 1. It performs a linear static analysis, which is known as the initial analysis. Eventually, it writes out a summary of the initial analysis. So right now, let me go and jump to that right now. And there are quite a number of results for this. Okay, so perfect. So here's the summary for the initial analysis. In this part of the F06 file, you're going to find a section called Design Constraints on Responses. There is a column called Value. These values are normalized constraints. These are not actually stress values or displacement values. These are normalized constraint values. And just to give you an example, I'll move the F06 file to the left, and here I'll apply this to one of these examples. So let's go ahead and refer to this normalized constraint value, 2.93. This normalized constraint value is referring to internal response ID 12 or 18, sorry. I'm using column 3. So here, again, I am looking at internal response ID 18. Remember that 18. If I scroll further down in the table, there's a section called Responses in Design Model. Take that at 18 and start looking in column 1. Look for internal ID 18, and here it is. Look to the very far right. This value here is the actual von Mises stress value, 69,000 psi. So I should actually change this to 69,559 psi. And right now, let's go ahead and plug this into Google to perform the arithmetic for me. And we'll go ahead and see what we get. So we get 2.93, which is the normalized constraint value that we saw a moment ago further up in the table. So let me go up there and go to 18. Oh, sorry. It's very important that you look at column 3, the internal response ID column. You saw how I almost used column 1, which is not the correct column to use. Always use column 3 here. So response 18, and here we have the value of 2.93. So perfect. Now you know how to compute the normalized constraint. Let me go ahead and flip back to the user guide. And a few comments about the normalized constraint. Or rather, let me actually jump to a table on page 47. So now that it normalizes all the constraints, displacements are normalized, constraint or stresses are normalized, how does it handle these normalized constraints now? Any normalized constraint under 0 means that constraint is satisfied. So if you get a negative normalized constraint value, that's a satisfied constraint. If it's a positive normalized constraint value, that means the constraint is being violated. When MSC Nastran has over 336 normalized constraints, it performs a truncation. So there's a cutting line where it says, okay, the other constraints can be ignored, but the constraints above the threshold, I'm going to retain, and I'm going to keep those in mind while I perform this design cycle. There's also one constraint, normalized constraint, that's higher than the other ones. That one's known as the maximum normalized constraint value. So if I go back to my F06 file, again, if it's a negative normalized constraint value, that means it's a satisfied constraint. But if it's a positive or above 0 constraint value, that means that constraint value is being violated. Here, the double asterisk indicates that that represents a violated constraint, or rather a maximum violated constraint. So you see here, it's marked both of these normalized constraint values as the maximum. Here, you can already see that if I trace this to internal response ID 3, let's go ahead and track that to response 3. That would be this one. You see it is referring to response label R2. Remember that R2 later on, actually. Also here, in the upper bound, you get these V's. These are actually saying that these regular von Mises stress values are actually violating the bound. Hence, we have the letter V. And here, a little bit above, there's actually a little table saying if it's a V, it's a violated response. An active response, I can't recall exactly what the definition is, but if I recall, it means that it's everything above the threshold. So every bar that you see here is an active constraint. The highest bar, if you will, is the maximum constraint value, and the individual bars mean or represent each individual normalized constraint value. So this row is corresponding to bar 1, and then the next row is corresponding to bar 2. The next bar is corresponding to one of these bars, and so on and so on. This diagram is just something to give you a mental image. It's not the actual values plotted here. It's just an example. Now, great. So I've defined what a normalized constraint is. I've defined what constraint screening is. You have an idea of what a maximum constraint is, or rather, a maximum normalized constraint. You have an idea of what a violated and an active constraint is. And now if we keep looking at the F06 file, you can see right off the bat for our constraint labeled R2, a lot of the elements 2, 3, 4, 5, 6, and so on, have von Mises stress values that are violating the upper bound. But this is the initial analysis. Let's go all the way to the bottom. We find that the optimization terminated after design cycle 19. Now, if we scroll up a little, we have the normal final summary. I should point out that in the summary of the design cycle history, there's a column called maximum value of constraint. These values, again, are normalized constraint values. These are not von Mises stress values or displacement values. These are normalized constraint values, as I explained a little bit earlier before. And now let me move this to the right and explain where these values actually came from. Here on the left, I have a summary of what MSC Nastran does during each design cycle. In design cycle 1, it performs the first linear static analysis. As the summary table a little earlier showed, the maximum normalized constraint value was 2.93. After it performs the optimization, it creates the approximate model. It then performs a second linear static analysis at the beginning of design cycle 2. This linear static analysis produces a new maximum normalized constraint value, and that is reported in the following row that I'm highlighting now. After that, it performs the optimization. A third linear static analysis is performed. This then produces a new maximum normalized constraint value, as I'm highlighting here on the right. And it does this again and again, approximately, 20 times, as you see here, 20. So 1, 2, 3, you keep counting down, you'll get all the way down to 20 here. Now, usually when you're trying to track which constraint is causing the infeasible design, you want to look for at least 1 or 2 constraints that are being violated simultaneously. As I mentioned earlier too, in the example of the graph, we had 2 constraints that were being violated simultaneously. And now we're going to hunt for that here in the F06 file. So let's keep scrolling up. We start seeing the summary of design cycle 19. So let's go to the very top of that. So here's the summary for the final linear static analysis. We see, if we scroll down, we have our design constraints. Let's look here what's going on. We have multiple elements that have a positive normalized constraint value of 1. So here, internal response ID 2, 3, 4, these are all a value of 1. And let's go ahead and just take maybe this one here that's marked with an asterisk. So we'll take the 2 here in column 3. We'll trace it down to the response of the design model. And here's internal ID 2. Again, it's at the end of the 19th design cycle. It's found that the stress value of 0.06 psi is still violating the von Missy's upper bound of negative 36,000 psi. And then here, if we keep looking down, it's R2 all the way down. So we have to review the upper bound for our R2 constraint. And here, if I look down, it's nothing but R2. Now let's go ahead and take a look at my web app. This web app, again, it helps you create your design model for MSC Nastran really rapidly. This is included in the more advanced training. Again, just a quick reminder, my email address is here. If you want access to this tool to generate your entire optimization model, please reach out to me. I'll be more than glad to give you access to this tool. Let's go ahead and look at the constraints I've defined, specifically the R2 constraint, which is the von Mises stress constraint. Here, my upper bound, or rather, prior to this, and here I'll open the BDF file just to prove it. Here we go. So here on the right is the design model I created at the very beginning. You can see that my design model actually has the upper bound set as negative 36,000 psi. But early on in the optimization problem statement, I said that my lower and upper bound should be negative 36,000 psi, which is correct, and the upper bound should be positive 36,000 psi. Here I have accidentally added the negative symbol here. My design model has the negative symbol, unfortunately. This is what's causing what's the word I'm looking for? It's not expected, or rather, it's not reasonable to have a pure negative von Mises stress value for this cantilever plate. It's just not realistic. So now I have to correct this. So let's go ahead and minimize all of this. I'll go ahead and I'll duplicate my optimization working directory, and I'll call this _B. And then in here, I'll open the design model. So here's my design model. And what I'm going to do, I'm going to replace the old constraint entities here. And then here, let me just delete the whole section. And what I'm going to do now is I'm going to correct the upper bound. I'm going to remove the positive, and here it's updated automatically. I'm going to take these updated Nastran statements and plug those back into my design model. And then I'll go back here, and then I'll delete the old optimization results. And then I will go ahead and run Nastran. Let me navigate to that updated directory and select this optimization model, and then we'll perform the optimization again. And then I most likely had an issue with memory. The reason I'm having an issue with memory, I am working on a virtual machine, and I have purposely given this machine a small amount of memory. So let me go ahead and just close out some of these programs that are not essential, and then I'll go ahead and repeat the process again. So let's go ahead and run that optimization again. And we'll let that finish up in a moment or two. While that's happening, let me take this notepad view and show this side by side. So here on the left is the original F06 file where I encountered the error message, a best compromise and feasible design message was shown. And let me go ahead and on the right show the new F06 file after we've gone ahead and made the modification. So now we get the message. the golden message that says run terminated due to hard convergence at an optimum or an optimum point, that is. So there you have it. Let me go back to the summary or my agenda. So there you have it. That is how MSC Nastran handles constraints. We've gone ahead and resolved our first issue where we arrived at a best compromising feasible design. We covered what this could look like if we were dealing with a simple three-dimensional function. If you recall at the beginning of the video, in this case where we had two ellipsoids that did not overlap, a solution of x1, x2 that satisfies both constraints just did not exist. So MSC Nastran arrived at a best compromising feasible design. After we fixed the error for these two ellipsoids and then found a solution, we leveraged the same methodology for my cantilever plate, hence these F06 files. We went over normalized constraints. We saw how MSC Nastran deals with hundreds of constraints. It just normalizes each one and then performs a constraint screening. Everything under a tolerance is essentially ignored, but everything above that is considered during the optimization process. And I should note that for each design cycle, the maximum constraint that dictates the optimization cycle will change from design cycle to the next design cycle. By this I mean in one cycle it could be displacement that's dominating. It's just being severely violated. But then the optimization fixes that constraint, but now the stress value is being violated. So you see that jump again and again. We saw how to track the maximum constraint value in the F06 file. We saw how to distinguish between normalized constraint values and normal structural responses such as displacements and stresses. We saw that in the summary table at the very end. We saw that the column here on the far right, these are actually normalized constraint values. And the last thing I'll leave you off with is that, or the last two things I'll leave you off with, when you use Excel to plot your tables, yes, you're familiar with the objective and design variable tables. When you plot your constraint values, these values are actually the normalized constraint values. So if you want to know, or at least one of the only ways I know at this moment, to figure out which response is causing this normalized constraint value, you will have to go into the F06 file and track it down using the method I showed earlier. So again, the way you do that is you look down here, you find the maximum constraint value, you look at the internal response ID, and then you track that down to the responses. So that'd be here, and you find out that it's this is the displacement constraint that we've just tracked for this design cycle. And then again, the next design cycle, it could be stress.